So in today's video, we're going to be looking at measures of location. What does that mean? Well, we're going to be looking at different types of mean. We're going to be looking at the median. We're going to be looking at the mode. Okay, these are terms that you've probably heard many times before, but we're going to add on a few extra terms that you may not have heard of before, but they are very useful to us in statistics. So I'm going to start off with the arithmetic mean. That is the mean that we all know, okay? It's the standard average that we can take for a data set, okay? So there's two different ways of writing the mean in terms of notation. We can write it either using this weird symbol called mu, okay, it's a Greek symbol, or we can write it using x with a bar above it, okay? We call that x bar, okay? The difference between these two is we use mu whenever we are referring to a population mean. Okay, so if you are ever looking at the mean of a population, you're going to use that mu letter to denote that mean, okay? But if we're looking at a sample mean, so we've taken a sample of my population and I've just taken the mean from each one of my samples, okay, so I've taken the data from each one of my samples and taken the mean of those, that is a sample mean, and I'm going to denote that by x bar. So depending on what you're looking at, whether it be a population or a sample, depends on which one you are going to use in your notation for this, okay? In the same way, we're going to have a very slightly different notation when we actually do the equation for this. Okay. Both of these say the same thing, it's just that we use a different n depending on whether we are looking at a population or we are looking at a sample. What does this mean? Well, we know how to take an average, okay? You've done this many times before in high school, okay? When you need to take an average, you add together all of your data points and then you divide by the number of data points that there are. That's exactly what we're doing here, okay? I'm taking the sum, which is what this symbol is here. Okay, this is a summation symbol. I'm taking the sum of each of my data points, which we're going to denote by xi. So I'm adding together all of my data points and I'm dividing by the number of them that there are. Okay, the number of data points in a population we denote with a capital N, and the number of data points in a sample we denote by a lowercase n. Okay, that's the only difference, but both of these equations are saying the exact same thing. We're taking the sum of all of the data points and we're dividing by the number of data points that there are. So this is the normal average that we are used to. Okay, so for example, let's say, I'm just going to do a super quick example here. Let's say I wanted to find the average of 20, 30 and 40. Okay, I want to find the average of those three data points. Well, all I need to do is I'm going to add them together and divide by the number of data points that there are. So this would give me 90 divided by 3, which is equal to 30, which makes sense, okay? The average of those three, they're equally spread out. It's going to be the midpoint, okay? Whenever you do these, okay, most of the time when we do our means, we're going to be looking at sample means. So this would probably, I mean, we're only looking at 3 data points here. I would probably guess that that would be a sample, okay? You don't normally get a population of 3. But normally we're looking at sample means. So you would probably see this a lot more than you would see our Greek symbol mu, okay? You normally have an x bar in most of your problems that you're going to come across. Something else that we need to look at is something called an outlier. So an outlier, okay, is just a data value that is extremely different from all the other data values. Okay, a good example of this normally is when you're looking at people's height. Okay, normally let's say most people in a classroom, you'd say girls are probably around 5'5" most of the time, and a lot of the guys are normally around like 5'10" ish, okay, as an average. But you may have someone in your class that could be like 6'10", okay, someone that is way taller than everyone else. Okay, you could also have someone that is way smaller than everyone else. Okay, so these would be outliers. Okay, you normally find most of your data is clustered around some kind of centered point. Okay, they're normally clustered together, but sometimes you get a data point that is way different to all the others. Okay, and that would be an outlier. Some measurements that we use in statistics are affected by outliers and some are not. Okay, if something that we work out, let's say a mean or a median or a mode or something, is not affected by an outlier, so outliers don't affect the value of that particular statistic that we're taking, then it is called a resistant measure. So a resistant measure is a measurement not affected by outliers. It's a measurement or a summary statistic that is not affected by an outlier. Okay. Now, the first thing that we've looked at here is the arithmetic mean, okay, the normal mean and average that we're used to taking. Is that a resistant measure? Okay. Well, if instead, let's come back to my small example here, okay. If I had instead 20, 30 and 140, okay, that 140 would be a major outlier. It's way different to my other data points, which means that my mean of 30 would change dramatically. Okay, so an outlier does affect the mean by quite a lot, okay, especially when you only have a small number of data points. An outlier can really affect that value. Okay, now when you have a lot of values, an outlier may not affect it as much, but it is still going to change that value of the mean. So a mean is not a resistant measure. An outlier changes its value, and sometimes quite significantly. So the mean is not a resistant measure. Because it is affected by outliers. Okay. Now, one other thing that we need to look at, another type of mean that we're going to look at, is called the weighted mean. The weighted mean is very similar to an actual mean, okay? The problem that we now have is that each data point carries a different level of importance to the others, okay? So when we calculated the mean before, we just took each of our data points, we added them together and divided by the number of them that there were, okay? Each one of those had the same amount of input to the mean as every other data point, okay? One data point was not less important than another, okay? They all had a weight of 1 because we added each one together. We just used that data point once and we divided it by the total number of data points that we had. With a weighted mean, each data point has a different level of importance, okay? So some data points actually are worth more to the mean than others. A classic example of this is when you actually do your grades for each class, okay? When you get a grade for a class, it's not just made up of assignments where every single assignment had the exact same weight, okay? You normally don't find that one homework assignment is worth the same as a test, which is also worth the same as your final exam, which is also worth the same as a quiz, okay? Each one of these things has a different weighting in your class depending on how important that assignment is. That's the classic example of a weighted mean. And the way that you calculate a weighted mean is slightly different to how we did it before, okay? So the weighted mean is used when each data point carries a different level of importance. So the way that it's calculated, we tend to use X bar, that sample mean notation, we tend to use that to also denote our weighted mean, okay? You never really see mu used in this, okay? We tend to denote it also by X bar. And the way that it is calculated, I'm going to do this algebraically, but then we can talk it through. Okay. What we do, each one of these W's is a weight, okay? It tells me how important something is, okay? The higher that W is, the more important the associated data point X is, okay? So if W1 was your largest W that you had, okay, that would mean that this data point X1 is the most important data point that I had. For example, normally in a class, let's say your final exam is worth the most of any assignment that you have. In which case, your final exam grade that you got would be X1, and W1, let's say, would be its associated weight, but it would be the highest value of any of the W's, okay? Now, W1 isn't always the highest value, okay? I'm just using that as an example, but I'm just saying here that the most important data point will have the highest weight, okay? Whether that be W1, X1, or if we're looking at WN, XN, okay? Just whichever XI has the most importance has the highest WI associated with it, okay? And then what we're doing is we're taking each of the weights, multiplying it by its associated data point, and we're adding those all together. Okay, so for example here you could have, let's say, each of your grades for like a final exam, your average homework grade, your midterm test grade, your quiz grade, and then we're multiplying each one of those by its associated weight. Okay, so you could multiply it by the percentage. Let's say your final exam's worth 20% and your homeworks are worth 30%, and you can keep going, okay, whatever each one is worth. And then at the end, once you've added all of those together, you're going to divide by the sum of the weights. Okay. Now, if you were using percentages, when you calculated this, your weights would probably add up to 100, okay, 100%. Or normally what we tend to do is we try to make the weights add to 1. Now, this is not always the case, as you will see in a second, but 9 times out of 10, when we try to do a weighted mean, those weights add to 1. So we try to get the weights add to 1, but not always the case. Okay. So all we do here is we take a data point, multiply it by its associated weight, add all of those together and we divide by the sum of the weights. Now I want to do this example. This is an example of a weighted mean where they have done this for grades. Okay, so exactly what I was just saying. And we've got a girl, Megan, we've got her grades here, okay, for 4 classes in her freshman year. Okay, she's taken Psych 101, Probability and Statistics, Anatomy 1 and English 101. Okay, and it tells us the number of credit hours this time, because we're doing different classes this time, and each class is worth a different number of credit hours, which means each one is going to affect her GPA differently. Okay, and we've got the grades that she got in each one of those classes, and each grade is worth a certain GPA. Now we're just dealing with whole numbers here. We're not going to deal with decimal values if you get like an A- or a B+ or something. Okay, we're just dealing with whole numbers. So anything on the A scale is worth 4 points, anything on a B scale is worth 3 points, and anything on the C scale is worth 2 points. And the question is to calculate Megan's GPA using the credit hours as weights. Okay, so what I have done here for each one of her grades, so she got a B in Psych, which is worth 3 points, an A is worth 4 points, a C is worth 2 points, and an A is worth 4 points. Okay. So she got 2 A's and a B and a C. Now the issue that we have here, which you can see from her grades, her Anatomy 1 class, she got a C in, but it was worth 5 credit hours. It was her highest weighted class. Okay, so the better she could have done in that class, the more it would affect her GPA. Again, the worse she would have done in that class, then it's going to affect her GPA negatively in a larger way. Okay, so she really needs to do well in that 5 credit hour class, because it's really going to help her GPA if she does that, because it's worth more than the others. So when you work out this weighted mean, you take each of the grade points, so I would take 3 in this case, and I would multiply it by its weighting, the number of credit hours. Then I would take 4 multiplied by 4, 2 multiplied by 5, and 4 multiplied by 3. So each one of my grade points is multiplied by its weighting, the credit hour. Then I add all of those together, and I divide by the sum of the weights, so the sum of the credit hours. And she took 15 credit hours in total if you were to add all of those together. So when you work this out, you end up with 3.13 is her GPA from this semester. Another type of problem that you can get is where they say, okay, here is the GPA that she really wants. What grade does she actually need to get in a particular class in order to get that GPA? So they have said, okay, we're going to keep the other grades the same, but what would she have needed in Anatomy 1 in order to pull her GPA up to a 3.4? So instead of getting a C, what did she really need if she wanted that 3.4 GPA? Well, we start out saying that her weighted mean is 3.4, okay, because that's the weighted mean that she wanted. Then again, I go across and I say, okay, I'm going to multiply each one of these grade points by its weight, the credit hour. And when I get to that Anatomy 1 class and figuring it out for that, I'm just going to call my grade point X, okay, because I want to know what X is. I want to know what grade she needed in that class, okay? So if I can figure out the grade point, I can then figure out the grade. So I'm going to call it X, and I'm going to multiply it by the 5 credit hours that grade is worth. And then I've got my final class. And I've divided it again by the sum of the weights. When you do that and you simplify it, you should get down to this here. Okay, so I've just combined each one of these together and added them up. And then I've simplified that to just 5x divided by 15. Now you're just solving for x. So I've multiplied both sides through by 15. Then I've subtracted 37 from both sides, and then I've divided by 5. And that tells me that x is equal to 2.8. Now again, we are not dealing with decimals in this example. We are only saying that each grade is worth a whole number. So in this case, if she would have gotten X is equal to 2, which was a C grade, it is not enough to get to her 3.4 GPA. We already knew that because that is what it told us at the start. But if X was equal to 3, we know if she got a B that it would be high enough to tip her over to at least a 3.4 GPA. So what she really needed in Anatomy 1 was a B to ensure that she had a 3.4 GPA that semester. The next type of mean that I want to look at is called the trimmed mean. Okay. What this does is sometimes you have some outliers that you would really like to get rid of, and you just want to concentrate on the main bulk of your data that is clustered together and kind of forget about the outer edges of your data that are kind of a bit too extreme, okay, to really worry about almost. So what they tend to do is they do something called a trimmed mean, and it's normally a percentage trimmed mean, so like a 10% trimmed mean, a 20% trimmed mean, etc. And what that does, let's say you had a 10% trimmed mean. Okay, a 10% trimmed mean would get rid of your top 10% of data and your bottom 10% of data. Okay, so if you had 100 data points and they said to you, find the 10% trimmed mean, okay, 10% of 100 is just 10. So I would get rid of my top 10 data points and my bottom 10 data points. Okay, so 10% trimmed mean gets rid of the top 10% of data and bottom 10% of data. And then you just find the mean of the remaining data, okay? So again, if you had 100 data points and you were finding the 10% trimmed mean, I would get rid of the top 10 data points, the bottom 10 data points, and I would be left with the middle 80 data points. So I would then sum together those 80 data points and divide it by 80. I'm just finding the mean of those middle 80 data points, okay, or the middle 80% of however many data points you would have, okay. So I get rid of the top 10% of data and the bottom 10% of data and find the mean of the remaining 80%. There is one catch with the trimmed mean that you have to remember. Your data has to be in order first, from smallest to largest, okay? You have to order your data points first. Okay? If you don't order it, then taking away the top 10% and the bottom 10% doesn't mean anything, okay? Because you would actually be getting rid of some data points that are in the middle of your data that you're actually looking at, that you're actually worried about. So make sure you actually order your data first, because then when you get rid of the top 10% and bottom 10%, you will be getting rid of the outliers that you don't want. Okay, but otherwise it doesn't mean much. So make sure that you order your data first, and then you can do the trimmed mean, whether it be a 10% trimmed mean, a 20% trimmed mean. If it's 20%, you just get rid of the top 20%, bottom 20%, and then you look at the mean of the remaining 60%. Okay. There's an example here that we've got 10 data points here, and it's looking at how many text messages a person sends in a day. And they've given you these 10 data points, and they've said to find the 10% trimmed mean. Okay, you have 10 data points. 10% of 10 is just 1. So I'm going to then get rid of my top data point and my bottom data point. And then my remaining 80% is just my 8 data points in the middle. And I'm just going to find the mean of those, which is what I've done here. I've added them together and divided them by the number of them that there are, which is 8, and that leaves me with 24.625. Okay. Now the question is, for the next part, is the trimmed mean a resistant measure? So if it's a resistant measure, then outliers do not affect the outcome. And the answer is yes, it is a resistant measure, because when you take the trimmed mean, okay, as long as it is a large enough percentage trimmed mean, okay, and definitely a 10% trimmed mean would do this, you get rid of your outliers before you calculate the mean. So outliers do not affect the value of the trimmed mean because you are getting rid of them when you are trimming this data. So the trimmed mean is a resistant measure. Okay, the next thing to look at is the median. Okay, the median is just another measure of the center of the data, kind of like the mean is as well. Okay, it's a measure of central tendency. We're looking at roughly where the center of data is. We're just doing this in different ways. Okay, the average is one way of doing it, and another way of doing it is the median. So it's a measure of the center of the data. And all the median is the middle value. Now, it depends on whether you have an odd or even number of data points. So we're going to talk about that. But all the median is, it is the middle value. But again, same as we have with the trimmed mean, you must make sure that your data is ordered first. Otherwise, the middle value means nothing, because you could actually have your smallest data point in the middle or the largest data point in the middle if you have not ordered it first, which makes no difference, okay? It doesn't mean anything to us when we are looking at the center of the data if you take your smallest data point as the center, okay? So make sure that your data is ordered first, otherwise this does not mean anything. So it is the middle value when you have ordered your data first. Okay, make sure that you do order the data. Okay, again, it's very important when calculating the median. Okay, now there's two things that you have to be aware of here, and that is whether you have an odd number of data points or an even number of data points. If you have an odd number of data points, then you can actually find a middle value. Okay, let's say you have 5 data points. Okay, and they're in order. It's very easy to see that if I count my way in, this is the middle data point. I've got 2 on either side. So when you have an odd number of data points, you just take the middle value as your median. The problem arises actually when you have an even number of data points. Okay. Because in that case, let's say I now had 6 data points. Okay. There is no single point that lies in the middle. Okay. I don't have like 3 either side. Okay, I don't have 2 either side. Okay, it's not like symmetric about a central point. So what I have to do in this case is I take my 2 center points here. Okay, they're my 2 that land in the middle. I have 2 on either side of those. And I take the average of my 2 points that are in the center. Okay. So let's say that we came back here and we were looking at this data set here, I know I've crossed a couple of these out, but when we were looking at this data set, I had 10 data points, which is an even number. So I would have to count my way in. So if I did that, let's count our way in. So I've got 1 on either side, 2 on either side, 3 on either side, 4 on either side, and I'm left with these 2 data points in the middle. Okay, now they actually happen to be the same data point. So if I take the average of 23 and 23, I'm still going to get 23. So 23 is my median in this case. So when you have an even number of data points, just work your way in, and then it's the average of the 2 middle points. Next we have the mode, okay, and I've spoken about the mode very quickly in another video, and it is the most frequently occurring value. It's the value that occurs most often. Okay, so for example, let's go back to that data that I just had here. Okay, looking at our 10 data points. Okay, 23 is our most common value here. Okay, it's the value that occurs most often. Sometimes you can have more than one mode. So I can end up with a data set. I'll quickly come up with one. Let's say I had 1, 2, 3, 3, 4, 5, 5. Okay. I have 2 values that occur most often. I have 2 modes. Okay. If you have 2 modes, then your data is actually known as bimodal. Okay, because you have 2 modes. Also, if you have more than 2 modes, so if you have more than 2, okay, your data is actually called multimodal. So most of the data that you're going to look at will just have a single mode, okay? It's just going to be like the data set we just looked at. 23 was the mode. It was the most often occurring value, okay? It's a value that occurred most often. You normally just have 1 mode. Sometimes you do have 2 modes, and very rarely in stuff that we look at will you have multiple modes. Question with this is it a resistant measure? Okay. Do outliers affect it? Well, the answer is no. Outliers don't affect it. It is a resistant measure. Okay. Because outliers don't affect it whatsoever. If you've got these random values that are super extreme and nothing like any of the values that are clustered together, okay, then they're not going to be modes, okay? They're outliers for a reason. They're not like your other data points. So outliers do not affect the mode. They do not affect the data points that occur most often. So the mode is a resistant measure. It's resistant to outliers. The mode is also the only measure that can actually be applied to qualitative data. Okay, when you have data that is in words, okay, instead of just numbers, it's the only one that you can really use in that situation, because you can have something like a modal color. Okay, let's say you were looking at colors of cars in your neighborhood. Okay. You can have a most often occurring car color, okay? So the mode can actually be used on qualitative data. Most of the stuff, again, that we're going to do is going to be quantitative. We're going to be dealing with numbers, but just know that it can be used on qualitative data, okay? And very occasionally, again, you'll be dealing with something that has no mode, okay? If every single data point occurs once, then there's no mode, okay, because everything occurs with a frequency of 1. So if every data point occurs with a frequency of 1, so it just occurs once in the list, then there's no mode. Okay. So the next thing I want to look at is the relationship between the mean, the median, and the mode. So when we looked at this before, let's say you've got a histogram of your data. Okay, so you've put your data into classes, however many classes you've got. And once you've done that, you've looked at the frequency, so how many of your data points fall into each of these classes, and you've drawn yourself a histogram. The question is, where do the mean, the median, and the mode lie on that histogram, roughly? Where do they lie on that histogram in relation to one another? Okay. First one that we're going to look at is when you are looking at symmetric data. So if you have a histogram that follows that bell-shaped curve, okay, so again it's going to have the bars under it for each one of your classes, okay, so it's going to look like that underneath it, of course, but it's going to follow this bell-shaped distribution curve. In that case, when you have symmetric data, if it is perfectly symmetric, then right down the middle is all three of your values. The mean will actually equal the median, which will actually also be equal to the mode. So if you have perfectly symmetric data, those three values are the same, okay? Because that particular class will have the central tendency of the mean, okay? It will contain the average. It will also contain the center point of the data, the median, and it will also be the most often occurring class. So when you have perfectly symmetric data, the mean is equal to the median is equal to the mode. Now we have to deal with whether we have positively skewed data or negatively skewed data. So let's start with positively skewed. Remember, positively skewed means that it's skewed right, which means that most of your data is on the left. So positively skewed means it looks like that. This one was symmetric. Okay, for positively skewed data, okay, again, this is going to have those bars under it to represent each of the classes. But in this case, the mode is less than the median, which is less than the mean. So the mean is actually the largest value, followed by the median, followed by the mode. So it actually looks something like this. So here would be the mode. The median would be roughly here. And then the mean would be the largest out of the three values. So in that case, the mode is less than the median, which is less than the mean, okay? The mean is the largest out of the three values. And if we have negatively skewed data, so again, negatively skewed means this time it's skewed left, which means that most of your data is on the right. So it's going to look something like this. This is negatively skewed. Okay. And in this case, the mean is actually your smallest value and the mode is the largest value. So the mode, again, the mode is always at that peak, okay, because that's the most often occurring point. Remember, it's the one with the highest frequency. It's the one that occurs most often. So the mode is always at the top of that peak. So this would be your mode, which is the largest in this case, followed by the median in the middle again, followed by the mean. So when it's negatively skewed, then the mean is less than the median, which is less than the mode. Okay. A good way to remember it, okay, with negatively skewed data, as long as you can remember which one's negative, which one's positive, with negatively skewed data, these actually go in alphabetical order, okay? So it goes mean, then median, then mode, okay, with mode being your largest value when you have negatively skewed. When you have positively skewed data, they're in reverse alphabetical order. So the mean is actually your largest value, the mode is your smallest value, but they're in reverse alphabetical order, if you want a way of remembering which order they go in. Just kind of a summary of what we've been looking at. We have here a quick table that shows you which one is a resistant measure and which one isn't, okay? So we can see here that the median, the mode, and the trim mean are not sensitive to outliers, okay? But the mean is very sensitive to outliers. You put an outlier into your data set and it's going to skew the mean quite a lot. Okay, so it is not resistant to outliers. It is not a resistant measure, but the other three are, okay? The median is only going to slightly change if you add in one very large data point at the end, okay? But the median is more about the number of data points than it is about what those data points actually are, okay? Because all you're looking at is the very center of the data and looking at what the data points are right in the center. What the data points are on the outside doesn't really matter. So if you've got an outlier in there, it really doesn't make any difference. The mode and the trim mean, again, we have looked at, they are resistant to outliers, okay? Outliers do not affect them. Then we've got here whether you can use the mean, the median, the mode, and the trimmed mean for qualitative or quantitative data, okay? So next we would like to look at the moving average. This is just another type of mean, but this time we are looking over consecutive time periods and taking the average of a particular thing over those time periods. So a classic example of this could be looking at gas prices over a certain number of years, or we could look at the average number of games won by a certain team over consecutive years, okay? Let's do a quick example to kind of show this. So let's say we're looking at the years 2000, 2001, and 2002. Okay, and let's say that I've got a particular sports team and I'm looking at the number of games that they won in each year. So let's say that this particular team had, let's say, they won 10 games one year, and then the next year they won 12 games, and then the following year they won, let's say, 17 games, okay? And we want, in this case, the 3-period moving average for 2002, okay? I always take, they'll give you the number of periods that they want, okay? So in this case, we'll look at a 3-period moving average. We want 3 time periods to take an average over. And it's always for the time period that is the last one, okay? So I want a 3-period moving average for 2002. That means that I look at the number in 2002 and I look at the numbers for 2 years prior to that to give me a 3-period range. Okay, so I'm looking at 3 periods and I'm going to take the average over those 3 periods, going from 2002 and back so that I've got 3 periods within my average. Okay, so a 3-period moving average for 2002 would be 10 plus 12 plus 17 divided by 3, which would be 39 divided by 3, which is 13. So my 3-period moving average for 2002 is 13. If I wanted the 2-period moving average for 2002, I just take the number that I observe in 2002 and the period before it, because I only need 2 periods now. So I start at 2002 and work my way back so that I have 2 periods. So I'm just looking now at 2002 and 2001. Okay, I'm only doing 2 periods, working backwards from 2002. So the 2-period moving average for 2002 would be 12 plus 17 over 3, and that works out as 29 divided by 3, which if we type that into a calculator comes out to 9.67 if we round it. Okay. If I wanted the 2-period moving average for 2001, I would take the number that I see in 2001 and the period before it. Okay. If I needed a 3-period moving average for 2001, I would need more data. I would need the data from 1999, okay, in order to get a 3-period moving average for 2001, because I start at 2001 and I work my way backwards so that I have 3 periods. So I would need 1, 2, 3 if I did a 3-period moving average for 2001. Okay, so you always start at the time period that they give you. In this case, we were looking at 2002, and you work backwards from that time period so that you have the correct number of periods that they're asking for, and then you just take the average over those periods. That is a moving average. Okay. The smaller the period that you're looking over, so if we're looking at a 2 or 3 period moving average, it will be closer to the average for that particular year that they are asking for, as opposed to if you look over many, many years, okay? It's more likely to fluctuate if you have more years and you're looking over more years and a longer period of time, okay? Because let's say I wanted a 10-period moving average for 2002. Well, this particular team may have done really, really badly 10 years prior to 2002. Okay, so if I took a 10-year moving average, it's probably going to be vastly different from this 17 value that I have as the number of games that were won in 2002 if I took a 10-period moving average. Whereas if I'm looking in a smaller amount of time, so I'm only looking over 2 or 3 years and taking the average over 2 or 3 years, it's much more likely to be closer to the value for that actual year than if I looked over a long period of time. Okay, so now I want to look at how we do some of this stuff on the calculator. So how can we calculate the mean and the median on a calculator? Okay, the first thing that you need to do is make sure you have a clear screen, and then I want you to go to this button here that says Stat. Okay, now what you can do, rather than sitting there and adding together a bunch of numbers and then dividing by the number of them that there are to find the mean, what you can actually do is actually create a list of these numbers, and then your calculator will do all of that for you and more. Okay, it will actually calculate multiple things at once for you. So when you go to that Stat button, if you actually click on the first tab that we have here, click Edit, so click the first option that you get. Okay. Now, what this will do is it will bring up some lists for you. Now, hopefully you don't have anything in these lists, but if you do, just click this up button, the up arrow, so that you are at the name of the list, and then you can click clear and it will actually clear the whole list for you if you need to do that. Okay. But what you can then do is just put a list of data in and it will calculate the mean for you. So what we're going to do is just create a random list of numbers, and we're going to see what it does when we calculate the mean. So let's do 1, 6, 7, 4, 9, and 15. Okay, so I've just created a random list of numbers and I want to find its mean. So what I'm going to do is I'm going to quit out of this menu. So just go to second and mode and it will quit back to the main screen. And then if you go to stat again, click across to calc, and then that first option there, one variable stats, you're going to click on that. And now it's going to ask you for two things before you calculate. It's going to ask you for a list and a frequency list. Now, if you are just calculating a mean, okay, just the standard mean, or if you need to do a moving average, you would just put whichever list you've used for your list of data, you put that in that first list here, okay? So we put all of our data into list 1. If you used a different list, all you need to do, you'll see above each of your numbered buttons are actually the list names. So all you need to do is go to second and then click on whichever list that you put your data in. Okay, so you'd just go to second. If it was in list 2, you'd click number 2. If it was in list 3, you'd click second and 3. Okay. Now for a standard average, you leave your frequency list blank. Okay, don't put anything in there. However, as we'll see in a second, if you are doing a weighted average, a weighted mean, then we're going to put something in that frequency list. But right now you're going to leave it blank. So make sure if there is anything in there, you clear it. And then you go ahead and click calculate. And it will come up with all of this data for you. Now, some of this isn't going to make much sense right now, but as we go through this course, you're going to see some of this stuff time and time again. So it's actually a very useful tool to have. Okay. Now at the top, we have this thing X bar. Okay, remember that is our mean. So we know that our mean is 7. So the mean of our data list was 7. It's calculated that for us. We didn't have to add anything together. It did all of it for us. We have the number of data points that we had. We've got the minimum value that was in that list. We're going to come back to what Q1 and Q3 mean in a second. We have our minimum and maximum value, and then this value here is our median. So the median of our data was 6.5. That is super useful because, as I said when we looked at the median, what you have to do first is order your data before you would go ahead and calculate this thing if you were doing it by hand. Now we had an even number of data points. Okay, we had 6 data points. So not only would you have to go ahead and order your data points, you would then have to work your way in, find the 2 middle points because you've got an even number of data points, find the 2 middle ones and take their average. That is a lot of work. Okay, so this is way simpler. All you had to do was put your list in any order. It will automatically order it and it will find that median for you. Okay, so it's a super quick way of getting all of this information at once. So remember, at the top is our mean. That very top value is our mean. And if you work your way down, we get our median. Okay. Now let's say we wanted to do a weighted average. So going back to that example that we had previously, okay, where we looked at the student's GPA for a particular semester, and it gave us what each of the grades was worth as a point value, and then it gave us the number of credit hours that that grade was worth. So if you had a situation like that where you need to find that weighted mean, all you have to do is again go to stat and go to your lists. So click edit. I'm going to clear my list 1. And now what I'm going to do, in one of my lists, I'm going to put my list of points. So how much each grade was worth. Okay, so she got a B, an A, a C, and an A. So that was worth 3, 4, 2, and 4. Okay. And then in another list, I'm going to put my list of weights, so my list of credit hours. So her first class was worth 3 credit hours, her second class was 4 credit hours, that third class was that anatomy class that she took, which was 5 hours, and then the last one was 3 hours. Okay, so in my first list, I've got my list of actual data points, her grades, and in my second list, I've got my list of weights, which were the credit hours. Now, if I quit out of this menu and go back to stat and then go across to calc and again click on one variable stats, This time, make sure that you get these the right way around, okay? My list is my list of data points, okay? Again, that is list 1. It was the list of the grade points, okay? Now, her frequency list, that was her list of weights, okay? The weights always go in frequency list and the data points go in list, okay? So in whichever one was your data points, put that under list, and under frequency list, you're going to put the list that had your weights in it, which was our credit hour list, which I put into list 2, okay? And now I can go ahead and calculate. And as you see here, we worked this out previously, but it will give me my weighted average now at the top, okay? The rest of this data you don't have to worry about. We're looking at something that's got weights to it. We don't really worry about medians or anything like that right now. So all we're concerned about is if you need to do a weighted average, this is a great way of doing it to find that weighted mean. So the last thing I want to cover in today's video is percentiles, okay? Now, percentiles are just another measurement of where data lies, okay? Now, there's a lot of algebra involved in this, but hopefully you can follow along with this. We'll say that the pth percentile, I know that sounds weird, but that will be a value. So P is a value. P is just a value. It's like saying the fifth, okay? So the pth percentile, okay, I know it sounds weird. The pth percentile is a value, x, where p% of the data is less than or equal to x, and the rest of the data is greater than x, okay? So I could say, let's say I'm looking for the 20th percentile, okay? I'll find the value of the 20th percentile, and that means that 20% of my data is less than or equal to that value x, and the other 80% of my data would be greater than x. Okay, so the pth percentile is a value x where p% of the data is less than or equal to x, and the rest of the data is greater than x. Okay, again, we have to remember to order our data first. Otherwise, saying that something's less than or greater than doesn't make any sense when you haven't yet ordered your data. Okay, so make sure that when you do this, you order your data first. Okay, so we're going to order our data first. Now, when you do this, okay, you're going to be finding where that data point actually lies, okay? So what you're going to do when it says to you find a certain percentile, okay, you're going to be looking for the value. But the way that you calculate that value is by finding out the position of that value, okay? So what you're going to do is you're going to order your data, and then we're going to find the position of the pth percentile, whatever p may be. We're going to find the position of that particular percentile, and then we're going to look at the value in that position, and that value is our pth percentile. Okay, so we're trying to find the position of the data point that is at the pth percentile. Okay. So in order to find that particular location, we actually call it L, okay, for location. What you're going to do is first you're going to use a particular formula to find it, and then we've got to do some rounding, okay? So To find the location of that point, what you're going to do is this formula. Okay, it's not a very long formula, but all you have to do to find the location of the pth percentile, okay, let's say I'm looking for the location of the 20th percentile, okay, that means at that particular point, 20% of my data is less than or equal to that data point, and 80% of my data is greater than it. All I do is I take my number of data points that I have in total. So n is the number of data points, okay, and p is the percentile that I am looking for. So as I said, let's say you're looking for the 20th percentile, p would be 20. Okay, now you've got two different scenarios here. This value can come out to a whole number, or it may come out to a decimal. Okay, you are not always guaranteed a whole number when you calculate this location. So if it comes out to a decimal, round up to the next whole value, to the next integer. Okay, never round down. Even if you, let's say you calculated this and you got 4.2, you always round up. Okay, so I would round up to 5 in that situation. So whenever you do this, and if L is a decimal, always round up. Okay, so make sure you round up. So let's say you did this, okay, a particular example. Let's say you worked this out and L came out to 4.2. That would mean that I would round up to L is equal to 5, which would mean that that particular percentile, let's say I was looking at the 20th percentile, that particular percentile was at the 5th data point once I'd ordered it. Okay, so this just tells you the location of the data point. You then have to go to your ordered data and find the data point that is in that particular position. Now we look at the situation when L is a whole number. So when you go ahead and you calculate this formula, what happens if L is a whole number? What happens when it's an integer? Well, if L is a whole number, okay, so let's say I calculated this and L came out to 4, okay? I don't just look at the 4th data point, okay? What I'm going to do is I'm going to take that data point and the one above it and I average them. So if L comes out to a whole number, I take the average of that data point with the one above it, and that is going to be my pth percentile. Okay, so if L is actually a whole number, your pth percentile will not actually be a data point, well, it may not be a data point that actually exists in your data set. It's going to be the average of 2 of the data points. So if L is an integer, take the data point in position L and the data point in the next position, so in the L plus 1 position, I guess. So take the data point in position L and the data point above that and take their average to find the pth percentile. So it's actually easier if L comes out to a decimal in some ways, okay? But if L is an integer, just take the data point in that position L and take the data point above it and find their average, and that will be the pth percentile. Let's do a quick example. So let's say I've got the data points 3, 5, 0, 1, 9, 2, and 7, okay? Now, whenever I do this, I need to make sure that my data is in order before I look at any percentiles. So, putting those in order. 2, 3, 5, 7, 9. Okay, so I've put my data in order. Now let's say I want to find the 50th percentile. Okay, to find the 50th percentile, to find its location, I just find L is equal to, now I've got 7 data points here. I'm looking for the 50th percentile. So that is what my equation is. So if I work this out, it's 7 multiplied by 0.5, which comes out to 3.5. Okay. This is a decimal value, so all I have to do is round up. So I know that my 50th percentile is in my 4th position. Now, what do you notice about this? The 50th percentile is the same thing as the median. Okay? If I had what I've got here with an odd number of data points, the 50th percentile always works out to that middle value. If I've got an even number of data points, I'm taking the average of the 2 middle values for the 50th percentile. So the 50th percentile is actually always equal to the median. Okay? Because of the way that we calculate these percentiles, the 50th percentile will always work out to that middle value. Okay? We actually have another name for some particular quartiles, okay? Or some percentiles, I should say. They're called quartiles. The 25th, the 50th, and the 75th percentiles are called quartiles. These are the ones that you're going to see most often as we carry on in this course, okay? And they're actually labelled Q1, Q2, and Q3. So if you remember back to when we were just doing our stuff on the calculator for that list, and when we ran one variable stats, we looked at the fact that it gave us the median, but either side of that, it gave us these values, Q1 and Q3. So if you ever need to find the 25th or 75th percentiles, you don't actually have to go through using that formula here and then finding the actual position, because your calculator can do that for you for the 25th, the 50th, obviously for the median, and the 75th percentiles, okay? Those are called quartiles. They're the things that break our data up into quarters, okay? The 25th percentile has a quarter of the data lower than it or equal to it, and 3/4 of the data above it, okay? So all this does is it's going to break our data into quarters. So if you need to find that, you can just do it on a calculator, okay? You can just run the one variable stats on the list that you're trying to find the quartiles for. Okay. Another quick term is the interquartile range. Okay. The interquartile range is just what we call the upper quartile, Q3, minus the lower quartile, Q1. So it's my data point at the 75th percentile minus the data point at my 25th percentile. That's the interquartile range. What that does, if you think about it, this data point is at my 75th percentile. This data point is at my 25th percentile. Okay? Between my 25th and 75th percentiles, I have 50% of my data. Okay? Because at my 75th percentile, I know I've got 75% of my data lower than it. And at my 25th percentile, I know I've got 25% of my data lower than it. So between the two, I know that 50% of my data points lie between those two data values. Okay? So what the interquartile range does is it shows you how spread out the middle 50% of your data is. And if you remember in your Excel application 2 that you're doing, okay, the last problem was to draw something called a box plot. A box plot is based on quartiles, okay? So they actually did them vertically, but normally in textbooks they're drawn horizontally. And they looked something like this, but you just did them vertically rather than horizontally, okay? They had this kind of layout, okay? And we're going to see them again. But what these box plots show you, this value here at the end with this line that is drawn is the minimum data value. Okay, that line at the end tells you the smallest data point that you have, okay? And you always plot it against an x-axis, or in your case, as you did it, a y-axis when you did it on Excel, okay? But that shows you the smallest data point. Similarly, the line at the other end shows you your maximum data value, okay? Then the box in the middle shows you the quartiles, okay? The line in the middle of the box is your median, okay? That's Q2. So whatever data point is here, that is your median for your data. Then at either end, we've got Q1 and Q3, our lower quartile and our upper quartile, our 25th percentile and our 75th percentile. So the wider that box is, the more spread out the middle of your data is. The smaller that box is in the middle means that most of your data is clustered, okay? The middle 50% of your data is clustered together, okay? So it kind of gives you a good idea for the spread of the data, okay? Similarly, you know that if you've got these lines at either end that are way off, you know you've probably got some outliers somewhere. Okay, if you've got a really extreme minimum value or a really extreme maximum value compared to where that box is in the middle, you know you've probably got some outliers because your minimum or maximum are way different to where most of your data is clustered. Okay, so that's why we like box plots. It shows us the spread of the data. Okay, I know this was a long video and there was a lot in this. Some of this you will actually come across later on. It may not show up in this homework, but it's very useful to know for when we carry on. Okay, if you have any questions on this whatsoever, then please come to class or come to an office hour and ask. Of course, I'm always available by email, text or phone, so please ask me any questions that you may have, and I'll see you in the next video.